We're going to talk about certificate transparency today and how we can support this critical piece of internet infrastructure. This presentation is brought to you by two industry leaders, Let's Encrypt and myself, of course. There was going to be another logo here, but due to recent changes, I had to replace it. Although this is a networking event, we're going to talk about a few layers above layer 3 today, about a protocol that everyone is using, and this is HTTP, and it is used everywhere. There is a secure version of HTTP, HTTPS, which ensures that you are talking to the right server and nobody can read or change the data you are exchanging with this server. And over the last decade, we have come a really long way in terms of HTTPS adoption. And right now, it is Firefox reports that over 80% of the pages loaded with Mozilla Firefox are over HTTPS, while in some countries like the United States, it is above 90%. And looking at other statistics, we can see here the percentage of Google's traffic that is encrypted, and it is 95% right now. So almost all the traffic going to and from Google is encrypted and protected. In terms of Google Chrome, we see 93 to 99% across major platforms, and of course we have Linux at 81% as well for Chrome page loads. And in terms of time spent, users spend 95 to 99% of their time using HTTPS on Chrome across all the major platforms. So HTTPS, in order to work, relies on TLS. TLS is the protocol that handles encryption, authentication, and everything involved in protecting the HTTP sessions. It's also used in emails, like in SMTP, IMAP, etc., but primarily in HTTP. In order for TLS to work, it requires certificates, and because we cannot just install the certificate of every website in our computer, we only want to have a few tens or hundreds of certificates. We need some sort of PKI. And for TLS, for HTTP, this is called the WebPKI. And basically, this has a structure similar to RPKI, where the end user certificates for websites like GRNOG.gr are signed through a chain that ensures they are trustworthy, and you can authenticate the end server. The main difference with RPKI, however, is that in RPKI, for you to do something, you download a list of all active certificates. So once an hour, you go to these endpoints and you fetch every single active certificate right now. And then you process them and you do what you have to do with them. You either trust them or not, and you send them to your routers. In the WebPKI with TLS, you don't have a list of all the certificates. Every time you make a connection to a server, you receive a certificate, and this certificate is unique to that connection. So you may connect again and you may get a different certificate in some cases. So you don't have a list of all of them. The problem is that all these tens of organizations that issue certificates have about the same trust level. And there have been incidents in the past where one CA may have issued certificates for a high-profile website like google.com, for example, either because it was hacked, someone maliciously gained access to their systems, or there was some sort of misconfiguration, operational malpractice, etc. So we need to find a way to protect users against these attacks. We cannot just have them be vulnerable to any of these organizations. And this is why certificate transparency was created, and basically it involves a list of all a list of all certificates. We're trying to collect all the certificates that have ever been issued out there into some things that are called logs. where a CA, when it issues a certificate, it can send it to one of these logs, and then everyone can see that. And if you have a website, you can monitor those publicly available data buckets, and you can see if a certificate was issued for your domain names, for example, and you don't know about it. And you can then take action. These logs are cryptographically protected against tampering. So there are some security properties built into that. And over the past few years, they have been crucial to detecting problems with CAs, either accidental or not. And they have been of immense help in trying to make every internet user out there more secure. And now you may ask, if someone hacks a CA, why would they publish the certificate for everyone to see out there? And the answer to that is that some platforms like Apple and Google Chrome will not connect to a website unless the certificate appears in 2 or 3 minimum of these publicly available buckets. So it has to be there, otherwise there's no TLS connection. You never go to the HTTP layer. And other browsers like Firefox, for example, don't do that, so they would be vulnerable to something like that. But for the vast majority of web users, certificate transparency can protect their browsing online. Just to get an idea of the size of the WebPKI, there are about 4.8 billion certificates that have been logged in city logs, and over 500 million of them are currently active and not expired. So it's a significantly larger ecosystem than the RPKI one. And there are over 250,000 new certificates per hour. And to give you an idea, here are some pie charts. Let's Encrypt right now is the #1 CA with almost half of the currently active certificates, followed by DigiCert plus AWS, and then Sectigo, Google, Microsoft, and GoDaddy. And in terms of total certificates that exist in certificate transparency, Let's Encrypt is at 70%, and then everyone else follows right after that. So these are the 6 companies right now that are running city logs, and every CA has to submit every certificate they issue to at least 2 or 3 of them, depending on the certificate. It's a nice list of them. And from one of them, from Let's Encrypt, we have Phil here today with us to tell us what does it take to operate a city log. So Phil, feel free to share your screen and let us know.
My name is Phil Porada. I'm a software engineer here at Let's Encrypt. And prior to that, I've been a site reliability engineer for 5.5 years. For fun, I'm a network administrator and a systems administrator. I've been doing this from my parents' bedroom since I was a kid, basically. As of today, I've got a beautiful family with 2 baby girls and a ton of cats. So what is Let's Encrypt? Let's Encrypt is a nonprofit certificate authority that provides TLS certificates to over 325 million websites actively. We're supported primarily through corporate and non-governmental organization sponsorship. And to date, for .gr domains, we've issued almost 10 million certificates. We have written previously about certificate transparency. On the screen here, I've got some of those links for future review when you can download these slides. You can go check those out. This particular presentation will be a rehash of some of the information presented in those blog posts, with some additional improvements and some war stories. So we've mentioned logs, but there's also shards. So what's the difference? Each Let's Encrypt certificate transparency log is made up of many individual temporal log shards, and those are named after a period of time. Temporal, meaning that the log itself can accept certificates bounded from a start date and a end date. Each shard is technically a separate CT log, but they all share the oak or sapling family name. Oak being a production CT log, sapling being a testing CT log. So each shard that we deploy slightly overlaps with the previous shard while we monitor performance and ensure correctness. This overlap is a protection against possibility of any significant downtime as our certificate authority software folder switches between shards. We have had an incident in the past, back in 2018, where our software didn't roll over and we caused a slight outage for Let's Encrypt users. I think at the time there were 7 of us gathered around a hotel lobby table, investigating, running public communications, and deploying a fix. We've long since fixed that, and shard rollovers happen in the middle of the night without any engineers knowing about it. That's great. So how does a certificate transparency log benefit a certificate authority? Speaking as a certificate authority who operates a certificate transparency log, operating a log helps us take control of our own destiny. Apple and Google Chrome require that all domain validated certificates be submitted to 2 separate logs. And by running a CT log, we can fulfill half of that requirement for our own organization. For certificate authorities to do organization validated and extended validation certificates, the number of distinct CT logs increases. Let's Encrypt often issues more than 3 million certificates per day. So we set out to design a CT log infrastructure that could handle not only our high issuance volume, but the volume of every other publicly trusted certificate authority as well. On the screen here, you can see search. This is a public monitor that you can look up your domain or your specific certificate in and see which logs have a record of that certificate. And this is a tool run by Septigo. So we started our CT log journey sometime back in 2017. An initial feasibility test was done with Amazon and an RDS instance and EC2 servers. We used SaltStack to orchestrate much of that setup, and we learned how the pieces of the Google Certificate Transparency Go and Google Trillion projects fit together to provide what is known as the CT log. We've since destroyed those logs after learning how they work. So in 2018, we created the diagram that you see here on the left. This was our actual initial CT architecture. We did sizing and cost benefit analysis, arranged a deal with a physical server host. They had an EC2S provisioning system for 4 physical servers. And we continued to use SaltStack to deploy all the different bits and for a database to store the Trillion Merkle tree, which is the cryptographically safe storage for all of our certificates that get sent to CT. We used MariaDB Galera clusters. That particular set of logs turned out to be an operational nightmare for various reasons. We faced alert fatigue and a sense that it wasn't possible to run a successfully qualified log. Problems we encountered were frequent network failures. So at the front end, we implemented a BGP router that load balanced to several HA proxy load balancers spread across data centers, and from there, the various applications comprising the CET log. And that was a lot of fun, and it worked really well for failover. But we also faced server availability issues. When we would scale down a server, a new server that would have been available might not have been. And that was no fault of our own. That was just the particular provider that we chose to use at the time. And the last nightmare itself was the Galera cluster. Galera requires a very stable network, and especially if you are running a certificate transparency log that can grow upwards of 16 terabytes of space, and nodes fail, it takes a very long time to retransmit that full set of data across the network. So then we never made those logs publicly available, and instead we redesigned that infrastructure and chose to use Amazon Web Services again. We knew that Amazon would be relatively stable compared to our previous attempt. We were getting kind of burnt out on SaltStack itself, so we chose to use Kubernetes. We would have more automation and scaling available to us via that tool. So what you see in this picture is a basic network diagram, a way that we split apart our databases, and a view of the software running inside of a CT log from Kubernetes. So this infrastructure has only changed slightly since it was deployed in 2019. Oak and Sapling to date run in this type of system. So again, the software that we primarily run is Google's Certificate Transparency Go and Trillion. Amazon handles our database via RDS, but we're still responsible for the performance tuning, migrations, and monitoring. Certificate Transparency Go provides what's called a personality, and that is a Golang implementation of the Certificate Transparency RFC 6962. And it handles communication with the Merkle tree that's implemented by Trillion. So aside from running these particular containers, we run Nginx as a reverse proxy and have it provide path routing. We run Prometheus exporters for scraping metrics from hosts, databases, and applications. And we send alerts to our SRE team with Alert Manager based on those metrics. After running this particular set of logs for many years, I'd like to say it's hands-off, but it's not really the case. It took a lot of hard work to get here, and a lot of it relates to database operations, and we want to do our best to share that with you. So if you choose to run a certificate transparency log, you can get off the ground running much faster than we did. So our certificate transparency log grows fairly quickly. In a given year, a shard can get upwards of 6 terabytes. This particular picture shows the Oak 2023 shard, which is still accepting certificates. And you can see the spikes in daily growth rate over the past 90 days. And then Certificate Transparency Go implements an HTTP interface for interacting with it. And the active shard will always be performing the majority of operations. And you would think that maybe most of this traffic would come from certificate authority, but it actually comes from researchers, monitors, and transparency log mirrors running a specific endpoint called get entry, which is a way to download all of the data from a log. So let's encrypt for scalability reasons. We return at most 256 certificates with each request to get entries. And downloading the whole log from the very first certificate to the last will be the most significant demand of disk I/O on the database itself. And we had an incident related to that. Back in August of 2020, we performed a routine set of application upgrades and noticed the log line in the top picture. Thinking that that was a bug, we performed a rollback. We dug into the warning message. We contacted Trillion developers on Slack saying, hey, we saw this. What do you think? And it turns out that that particular error actually sweeps more serious errors under the rug, that Trillion was hitting max database connections. Why was that happening? It wasn't due to a Trillion bug. But it turns out that it was a performance problem induced by an abusive client that kept trying to request data out of our CT log. This person was launching multiple short-lived EC2 servers, bypassing our Nginx rate limits. The traffic peaked at 600 HTTP GET requests per second, which our database couldn't handle. Typically, we handle roughly 110 HTTP GET requests per second during those times. And this caused an outage not only for Let's Encrypt, but also for notably Sectigo for not being able to issue certificates for the duration. So we implemented a few quick mitigations to get us and Sectigo back into a functional state. The first of which was my favorite. It was returning a nastygram for the specific user agent and severely rate limiting their GET requests per second. The second mitigation was to set a global HTTP GET rate limit, and certificate authorities primarily post data into a log. So we knew that certificate authorities would be largely unaffected by this. And the final mitigation was to configure a max MariaDB connections parameter to limit saturating a database with connections. In the event that that would happen, the database driver would wait for an available connection before dropping off with an error to the user. So there is a cost of running a CT log. Obviously, the compute and storage and RAM and stuff, that's not free. But there's also the human time. Typically, Let's Encrypt spend about 3 months worth of time with 1 to 2 engineers a year doing routine maintenance, such as upgrades or troubleshooting. For compute, it can all largely be commodity hardware. Storage and RAM are negligible, just enough to run your applications. With EC2, that's even easier for us because we can spin up servers and spin them down as needed. The database, again, it's going to be your pain point. But horizontal scaling continues to be a solution there. And to a point, faster disk storage will help when more data is read from disks, such as when a monitor or a researcher is trying to download your whole log. And finally, I've got this wall of text about our lessons learned and takeaways. I'm not going to read this. You can review it at your own leisure at the end of GRNOG. Thank you very much.
Thank you, Phil. That's all very interesting. I have a few more slides, Andrea. Sorry for that. So let's go over a few things. As I mentioned earlier, these are the 6 companies that are currently operating CT logs. And you can notice a few problems with this list. The first problem is that it's just 6 of them. So this is very critical for everyone using the web online, basically. And we only have 6 operators of CT logs. And you need 2 or 3 of them minimum to be up and serving data to users. The other problem you may notice is that it's not a very diverse list. There may be some certain factors that make this a list that should be improved, and there should be more operators there, especially, for example, from Europe. So what you can do to help is you can run your own CT log. And this has a benefit for everyone out there. This is critical for web security and for monitoring certificate authorities better and helping them fix all the problems that come up. And it's required for like probably over 80-90% of HTTPS page loads. So setting up a CT log, Apple and Google have some guidelines, some requirements that you need to fulfill. What happens is you set up the infrastructure, then you send them the link, and then they check it for a few weeks or a few months. They make sure it's running, it's not doing anything weird, the uptime is fine, and if everyone is happy, you're happy as well, then you are included into this list of 6 organizations that operate these CT logs. There is a community mailing list that's very helpful. You can ask technical advice there, and there is a Trillion Slack channel that Phil mentioned earlier. However, as an additional gift to GRNOG members, there is this email address here that you can contact if you're even thinking about it and you need to learn more, if you need operational help, if you need to know if it's the right thing for you, if you need anything, I can help you. I can put you in touch with the right people, and I can get you started with operating a city log. And I'm sure Phil here and many others are happy to help as well and jump in the threads. And if you have perhaps a managed cloud service and you want to showcase that, like you offer managed databases and you want to tell the world how awesome they are, just run a city log to prove it. And if you want to showcase your load balancers as well and whatever you have, show us how good they are and help run critical internet infrastructure together. Thank you very much. That was all for today. We're happy to take questions if there is time.
Thank you, Adonis and Phil. Any questions?
Theodoros Polychniatis από Ripen CC. Adoni or Phil, I'm not sure if you can answer this question, but why only Safari and Chrome are checking the certificates of websites against CityLog? Why not Mozilla or Edge or other popular browsers?
So it is not just these two. There are a few other pieces of software that are doing this. I mostly mention these two in terms of market share. The reasons are not technical, is what I'm going to say. However, even if they don't check it and they don't protect their users at the TLS termination phase, they still benefit out of this. And Mozilla has been a great contributor, for example, to the ecosystem through their root program, and they heavily rely on city logs. So I hope this is a good enough answer.
Thanks.
Hello, this is Kostas Zogradelos. A question a bit related to what Theodoris mentioned earlier. So in order to have a real benefit out of it, you need your browser to actually consult the city logs. So my question is, who actually decides who is the one that enters the city log ecosystem that browsers actually use? So is it the 6 companies you mentioned? Is it just a subset of them? Who actually decides?
Phil,
that's going to be that's going to be Apple and Google Chrome, because they run a formal certificate transparency policy that includes all of the rules, the operational guidelines that must be followed by those 6 companies that Antonio has mentioned. I hope that answers the question. It's not the log operators themselves.
Thank you very much for the answer. It's not the answer I would love to hear, however.
Yeah, to add a bit more to that, perhaps, the city log operator chooses which CAs they accept certificates from. However, the list of CAs is mostly standardized. So Apple has a list, Microsoft has a list, Google has a list, Mozilla, Cisco, everyone has their own list, and they're mostly the same. And this list is generally accepted in all city logs. If the browsers do not accept a CA in the root program, then the certificates don't work anyway. So if I set up my own CA, like Safari wouldn't trust it. I have to go through a process, prove that I'm doing a good work, and then be included. I'm not aware of a city log actually excluding CAs right now. And it's up to the operators, however. There are some requirements around that, but it would technically, in theory, be possible.
Okay, I have a comment myself. I will take advantage of this and say I would like to raise awareness about Harika. HARCA is the Hellenic Academic Research Institutions Certification Authority. This is run by Aristotle University, I think, or GUNet. I'm not really sure. But it is a certification authority from our community, from the Greek community, and it is actually, it participates in all major root CAs, so in the browser as well. So it's not directly related to your presentation, but I would like to take this chance to raise awareness about this. Maybe we can invite them in future GRNOG to say a few things. Okay, thank you very much, Adonis and Phil.